Hey guys, sorry for have skipped two consecutive episodes. I was really busy. So yeah, I think let me check. Where should we resume from? So and so this will actually be Learning Kotlin Live episode 60, which is actually a Kotlin manual rating. We were at Curtain, and let's see if there's still something that we can learn from. We covered exception handling already. Select expression. I don't know if we should cover this. And shared mutable state and concurrency could be something that is a little bit too could be too hard for me. Let's see. Select expression is experimental as well, so I'm going to skip that as well. Shared mutable state and concurrency. I think this could be a little bit too hard, but let's give it a try. So coroutines can be executed concurrently using a multi-thread dispatcher like dispatcher.default. So that means that dispatcher.default has a lot of candidates. It presents all the usual concurrency problems. Yes, of course, because it's on multiple threads. The main problem being synchronization of access to shared mutate state. Some solutions to this problem in the land of coroutines are similar to the solutions in the multi-thread world, but others are unique. So here's the problem. Let us launch 100 coroutines, so doing the same action 1,000 times. 100 coroutines and do an action 1,000 times. We'll also measure their completion time for further comparisons. Okay, so massive run. What is massive run? Oh, so massive run is a extension of coroutine scope, and it does something. It takes in a suspend function of unit. It takes in an action, which should be an suspend function, and it does. It launched and coroutines and repeat k times. So and everyone is joined. Wait, jobs for each it.join. So and it waits for each item to be executed. So the counter is supposed to be 100,000, but it's actually 908, 9,800 and 627. So it's highly unlikely to ever print counter equals to 100,000 because 1,000 coroutines increment the counter concurrently from multiple threads without any synchronization. Yes, it's not synchronized at all. So basically, at least 1,400 times this counter is overridden. If you have an old system with 2 or fewer CPUs, then you will consistently see 100,000 because the thread pool is running in only one thread in this case. Okay, so that means that the default, because usually there are some best strategies for how many jobs and how many threads you would like to create on how many CPUs, and basically dispatchers.default would be run on n-1, I guess. So to reproduce the problem, you would need to do why? I don't know why, but it's not something we really care about now. I don't know why this is a way to. Oh, probably because with this the oh yeah, that's because of the difference between global scope and default context. Is there the full version? Oh, here it is. So basically, oh, here it is. Because empty context is a new fixed thread pool context which has 2 threads, and that's why. So sometimes we would try to fix this with volatiles when multiple thread and multiple core are in the play, but this does not fix this problem because let us try it. It's still, oh, it's helping a little bit, probably. I don't know. I think it's helping a little bit. Yeah, we see a 100,000 this time. Huh? Why? Wait. Oh, okay, finally. So it is indeed helping, but yeah, works slower. Oh, so it is working simply because it's slower, could be. Yeah, because volatile itself only promise reads and writes, but we're actually in this counter plus plus we're actually doing one read and one write, so it is still not it's still not so we can't simply solve this problem with volatile keyword. Where is it? Should be here. Here it is. Oh, so okay, in Kotlin volatile is an indentation. Thank you for that. That's helpful. So there are some thread safe data structures like the atomic integer and yeah, the atomic integer in Java, and I think this time this is going to work and always work. So yes, this is the fastest solution for this particular problem. It works for plant counters, collections, queues, and other standard data structures and basic operations on them. However, it does not easily scale to complex operations that do not have ready-to-use thread-safe implementations. So that means that there are some data structures that are not too complex and are not designed to be thread safe. So here is the thread confinement. Thread confinement is an approach to the problem of shared mutable state where all access to the particular shared state is confined in a single thread. It is typically used in UI applications where all UI state is confined to the single event dispatch application thread. So that means that just like the Android main thread, everything happens on the same thread, although nothing is promised, although the implementation itself is not thread safe, but by specifying everything to happen only on one thread, it is virtually thread safe as well. It's actually not thread safe. You're just trying to avoid all thread unsafeness. So let's see. Global scope dot massive run with context, counter context. Let's take a look at what counter context is. And the counter context is a new single thread context. So we can run all the coroutine on simply one. Oh, I forgot to take a look at the time that is used. Look, this is quick. This is super quick. This is super quick. This is a little bit slower because there is only one thread. Because there is only two threads, and there is only one thread. Oh no, sorry. There is a lot of thread, but for this case, it is only there's a volatile keyword, so it's a little bit slower. And for this case, there is no volatile, but the atomic integer has its overhead itself as well, so it's a little bit slower as well. But for this case, this is super slow. This is, look, it takes like 30 times. Am I calculating it correctly? Yeah, it's 30 times slower than those implementations. Because it does fine-grained thread confinement. Each individual increment switches from multi-thread dispatcher's default context to the single-thread context using with context block. So, yep. There's a fine-grained and a coarse-grained. I don't know what's the difference between these two. In practice, so my guess is this is probably a way that we're going to solve this super slow problem. In practice, thread confinement is performed in large chunks, e.g. big pieces of state updating business logic are confined to the single thread. The following examples does it like that. So it is not the whole block that only happens on single thread. It happens on multiple thread, but only with that we have the block synchronized. That's my guess. The following example does it like that. Running each coroutine in the single threaded context to start with. So yeah, it now works much faster and produce the correct result as well. Oh, it's a lot faster. Yes, and let's take a look at it. So it's running on new single thread context as well. So what's the difference? I don't see the difference. Oh, here. So here's the global scope.massive run with context, counter context, but this is the coroutine scope counter context. So what's the difference between these two? I wonder. I think it is with context. With context switch to another coroutine again, but this it's on the same coroutine, but just under the same context. Ah, interesting. So actually, I am not 100% sure what happens. What's the difference between these two? My guess is global scope itself is a coroutine, and this is a subcoroutine that runs on another context. But here we have only one coroutine. That's just my guess. Mutual exclusion. Mutual exclusion solution to the problem is to protect all modification of the shared state with a critical section. This is just like a synchronized block in Java. That is never execute concurrently. In a blocking world, you typically use synchronize or reentrant lock, yes. And coroutine's alternative is called mutex. Yeah, mutex, just like lock. It has lock and unlock functions to delimit a critical section. The key difference is that mutex.lock is a suspending function. It does not block a thread. Okay. There is also with lock extension function that conveniently represents mutex.lock and try something finally mutex.unlock. So my guess is this is going to be a little bit slow. Maybe 500 milliseconds. Yeah, it is also fine-grained, so it pays the price. However, it is a good choice for some situations where you absolutely must modify some shared state periodically. But there is no natural thread that this state is confined to, which means no nature. Oh, so you don't have a thread that you really want it to run on. You don't have a specific one. It can be run on any one, but you still want to make sure that there is a fine-grained. So what's the difference between fine-grained and did it ever discuss about this? I think this is the first. Oh yeah, this is the first occurring of fine-grained. So nah, and this is the last one as well, actually. So actually I know everything in this. Lovely. I hope I still know this as well. Actors. An actor is an entirely made up of a combination of coroutine. The state that is confined and encapsulated into this coroutine and a channel to communicate with other coroutines. Okay. I got something that I don't understand now. So a simple actor can be written as a function, but an actor with a complex state is better suited for a class. Looks like a synchronized object, maybe? There is an actor coroutine builder that conveniently combines actors' mailbox channel into its scope to receive messages from and combines the send channel into a resulting job object. What? So that a single reference to the actor can be carried around and as its handle. What? What? There is an actor coroutine builder that conveniently combines actors' what's mailbox channel. So we never learned about channel, so I feel like we need to skip this if we see any channel. Oh yeah. So yeah, channel is some experimental. We skip it because it's still experimental. So we probably should come revisit it someday, but maybe not now. So that's why I'm going to skip that part and the shared mutable gate and concurrency as well. So we still got 10 minutes, and I would like to take this chance to recap whatever we've learned in coroutine, or maybe, I don't know, is there a there's a guide, and I think there's a tutorial of coroutine. So how about that? Let's read this. This looks like interesting. So oh, actually this is a lot of comparison between other methodologies other than coroutines. So I don't think it talks it talks about a lot in coroutine. I don't think so. So maybe that's not something we're interested as well. Let's see. We've covered everything in coroutine except those that are experimental. Well, but I still don't feel like I am understanding coroutine enough, and clearly enough. how about this? So that is a really simplification of what we have learned, but maybe that's worth a read. So it's about, so no, these are just some um, Kotlin X 13 Core 1.0. Okay, that's really early. So these are just set up. I'm going to skip those. One can think of a coroutine as a lightweight thread. Yes, we have heard about this a lot. Like threads, coroutine can run in parallel, wait for each other, and communicate. The biggest difference is that coroutines are very cheap, almost free. We can create thousands of them, and actually millions of them, and pay very little in terms of performance. True threads, on the other hand, are expensive to start and keep around. 1,000 threads can be a serious challenge for a modern machine. So, at least in this tutorial, the main takeaway is coroutine is super lightweight, and that's, if you want something lightweight, you can use that could be a reason that you utilize coroutine. So so how do we start a coroutine? That's use the launch function. That's a coroutine builder we have learned in some earlier episodes. So this starts a new coroutine. By default, coroutines are run on a shared pool of threads. That's the dispatcher dot default, and it is a multi-thread pool, and it does not block. What else? I don't know. Threads still exist in a program based on coroutines, but one thread can run many coroutines. Yes. So coroutines are dispatched to these threads. So even if you have 1,000 coroutines, things can be run on. They are still run on like maybe 10 threads, or I don't know. I think coroutine has a default of dispatcher.default is n-1, where n is the core. Oh, or maybe the thread, the number of the processor. What's the name of that? The core, not the core. The thread. Is it called thread as well? Intel for, yeah, it's called thread. A thread. Here we start a coroutine that waits for 1 second and prints hello. So yep, it waits for 1 second and print hello, and sleep for 2 seconds and stop. So this 2 second is needed because global scope is just like daemons, and if you leave the main block, then this global scope would be cancelled as well. So we are using the delay function like thread.sleep, but better, it doesn't block a thread. Instead of blocking the thread, it dispatched to it yield the processing power to another thread, another coroutine, sorry, but only suspends the coroutine itself. The thread is returned to the pool while the coroutine is waiting, and when the waiting is done, the coroutine resumes on a free thread in a pool. The main thread that runs the main function must wait until our coroutine completes, otherwise the program ends before the hello is printed. This is what I talk about, the daemon analogy. Exercise. Try removing the sleep from the program above and see the result. It would only print start and stop. So let's move on. If we try to, oh yeah, there it is. Try to use the same non-blocking delay function directly inside main, we'll get a compilation error because Suspend functions can only be run in a coroutine. Suspend function delay should be called only from a coroutine or another suspend function. Or we can do probably the function dot async. I can't remember actually. Is it going to talk about it later? No, so maybe we can take a look at it by ourselves. I think it's in the composing suspending functions. Run blocking builder is a way, but we usually never use that. So maybe await. IT. Oh, the async block maybe. Async is async a builder as well. Where were we? Here. How about async delay? There's no async. Huh? What else did I spell? What? Wait, why? Huh? That's weird. Oh, it's still in a run blocking. So, no. I don't think this is going to compile. I don't know. Is it? I think it's running, just not doing anything. Because of broken, I don't know. Oh, actually. Could be that this is just too old. Let's try that on a playground. And so okay. Oh, I think it's going to stop. Yeah. But anyway. So yeah, we can delay in a sync block. So I don't know why this is failing here. Erase. But I think there's a way to run on think there's a way to run suspend functions blockingly. Oh, it's already 31. Is there... Is there a way to run suspend functions blockingly? Oh, there it is. Concurrent using async. It's still in run blocking. So async is just a way to get the callback, I would say. Oh, okay. That would be all for today. So let me go through the difference between async and launch really quick, and I'm going to end this. So basically, async is just like they're generally the same, but just the main difference is async is a way that you can return something that is inside the coroutine block, and with launch you only get a job, which you can dispatch it or just cancel it. You can't get the result. So that would be all for today. See you guys next time. Bye bye.